Hello, this is Mr. White, and this video is on increasing, decreasing intervals and the first derivative test, part 2. So here are the two exercises for this video. The first is more of a conceptual look and drawing an f-prime curve, and the second is where we get down and actually use all these calculus tools and rules that we've been developing thus far. All right, let's make these graphs a little bigger, and we'll tackle them one at a time. Okay, and for drawing the f-prime curve, generally we find it easiest to look at where the tangent line is going to be horizontal and recognizing that the derivative is 0 there. So it looks like the tangent line is going to be horizontal right here and right here for starters. And so at those two x values, we'll put a derivative of 0 here and here. All right, let's take a look at this stretch here. This looks like one that might be relatively easy to handle. That's a horizontal line. In fact, if we were to just come up with an equation for it, y equals 1, we know that if we derive that, we're going to get 0. And that makes sense because y prime equals 0. That makes sense because the slope of a horizontal line is going to be 0. So for that stretch, along that entire stretch of x values, we'll put a horizontal line of 0, or at y equals 0. So continuing to just try to work upward in level of difficulty, I might look at the other linear stretch as well. And again, because for lines, we know that the slope is constant at least. We know the derivative of any line is going to be constant. So looking at that line, I ask myself, what's the slope there? Well, there's a rise of 1, 2, 3 over a run of 1, 2, 3. So, and it's going downhill, so it's going to be negative 3 over 3, or negative 1. So let's put a stretch down here at negative 1. And let's recognize where we have some sharp points. Notice that we have sharp points here and here. That means that the derivative is going to be discontinuous. The slope, when I look, like for example, the slope right here is going to abruptly change when I go to this stretch right here. So let's denote that by saying there is no derivative right at this point, and therefore I need to put a little open circle at the end of my derivative curve. And likewise over on the right-hand side, I'll put a little open circle there. And let's now tackle the curves here. Again, given just the limited information we have, if we want to look at that and assume it's a parabola, that's not unreasonable here, I would say. Let's start by asking, what does the slope look like right when it stops along this stretch? What does it look like right along here? And let's just kind of visually eyeball that. Let's picture what that tangent line is going to look like. It may look something like that. And if I try to figure out what is that curve, or what is that slope roughly, I might look at a point here and say the slope is 1, 2, 3, 4 over 1, but it's going downhill, so negative 4. Now, if somebody else wanted to argue negative 5, or somebody else wanted to argue negative 3, you know, that's reasonable, but we're not trying to get that level of precision here. We just want to get the general shape of this curve. So I'm picking up down here at negative 4, and if we are assuming that this is a parabola, we know that for parabolas, we know that when we derive parabolic or quadratic expressions, we get linear expressions. We get something that is that is linear. So that tells us that the derivative curve should be linear along that roughly quadratic section. So we have 2 points, one here and one here. Even though one of them's open, we'll still just connect the dots. And due to the symmetry, and we'll assume that the slope here looks to be again at about a slope of 1, 2, 3, 4 over 1, roughly. So we'll put a point up here, and we'll connect the dots. Okay, now, is this a sharp point right here? I just hand drew this, and one person may see a sharp point, another may not. I didn't intend for that to be a sharp point, but you know, that's something that could be debated. I'm going to fill it in and say that we'll continuously go from a slope of 4 right here, roughly 4, and remember we said that we have a slope of 0 right at this point. And look at all the points in between. Notice all the tangent lines are steadily becoming smaller in slope. So it's steadily going from +4 down to 0. So let's just connect the dots here. And again, we're assuming we're visually approximating this as a parabola. Now, if we're to continue there, if that really were a parabola, this would continue all the way down to -4. And then there's that sharp point, so we'll put a circle. I have to admit, I'm looking at this picture and I'm going, does this really look like it has a slope of -4? It doesn't. Again, I'm not trying to nitpick on this type of problem. We're not going to try to nail you on that type of level of detail. So if you just left it like that, I'd say okay. If you preferred to adjust it a little bit and say, you know, that slope looks more like -2, so I'm going to put a circle here and connect the dots, you may do so. But anything that just roughly reflects that shape, that's what we're going for. This is our f prime curve. Okay, let's go on to the next one here. So this one, notice I intend for these to be sharp points, and down here these are supposed to be smoother transitions. All right, so that being said, let's look at the roughly linear sections here. And I'm going to pick one at random here. I'm going to say between that vertical line and this vertical line, I'd say we have something that is linear. Once I get down into this region, that's where it starts to curve. But right along here, we're going to say that that's a perfect line. And what is the slope of that line? Well, the rise looks to be 1, 2 over 1. And it's in the positive direction. So we'll say the slope along that stretch between those two green lines is +2. Okay, remember we said it's going to be a sharp point up here. So let's go ahead and finish our curve there, or terminate it there with an open circle. Let's look over here next. And again, I'm going to say that between these two curves, it's linear. This time it's in the negative direction. It's in the downhill direction. So we'll have a slope there, a derivative at -2. Now, as far as what happens in between there, that little curve stretch, we do have tangent lines that are going from -2 and are just gradually yet continuously transitioning up to a slope of +2. And it's in a very short span of time, right? It's only in between those two green lines. So that means my derivative curve needs to go from down here at -2. It needs to continuously go up to +2 here. And I forgot to put earlier, I should have done this right from the outset. I should have acknowledged that there's a 0 derivative right there, right? So let's go ahead and acknowledge those other, here are two more places where I have the horizontal tangent line. So again, if we're starting out, we may want to always start with those 0 derivatives. All right, let's go on. And we can tell that there's a repeating pattern here. This is a periodic function. So let's just try to speed it up a little bit here. A slope of -2. And then between here and here, a slope of +2. Open circle there, but continuously within a short span of time, connecting the dots there. And we can tell that that's going to repeat again over here. All right, so that is our f prime curve for this second graph. Let's go on to the next one. This is going to be just an application of the first derivative test within the interval from 0 to 2 pi, the open interval. And we did the first derivative test in the last video, yet I find that when we start introducing trig functions, students have a little bit of trouble adjusting typically. So I thought it was worth doing another first derivative test example or exercise with trig functions. I'll point out that we are looking on this interval from 0 to 2 pi. It's an open interval. There are parentheses there. And the significance of that is that we don't have to consider the endpoints. So if we ended up with some function that looked like this, we would not count these endpoints as being local maxima. Whereas if this had brackets, then we would say, okay, we are allowed to count the endpoints. We can consider those local maxima. All right, let's start by taking the derivative, of course. This is going to be pretty straightforward. You just have to do the quotient rule, right? So bottom times derivative of top, derivative of sine is cosine x, minus top, times derivative of bottom. And here I'm going to slow down a little bit because we need to remind ourselves that for taking the derivative of cosine squared of x, we need to remember that we need to conceptualize it as cosine of x in parentheses squared. And we see we're going to have the chain rule there, right? So when I derive that cosine x in parentheses squared, I'll bring the 2 down and put a 2 here, times the cosine of x in parentheses, now raised to the 1 power, times the derivative of that inside cosine x, which is going to be negative sine x. So again, that's just our chain rule at work here. Sine x. And barely get it on the screen there. All over the bottom in parentheses squared. Okay, now we're in search of critical numbers, but before I set this equal to 0 or undefined, let's go ahead and simplify it a little bit. Let's distribute this out. So we're going to get cosine x plus cosine cubed x. And then we've got a minus and a minus here. So that's going to become a plus. And then I've got 2 cosine x and then sine squared x. So 2 cosine x and then sine squared x. All over that bottom squared. 1 plus cosine squared x squared. All right. We may seem to be a little bit stuck here as far as what to do next. I mean, I guess we could go ahead and set this equal to 0 or undefined. But as far as what to do next, we may feel a little bit stuck until we recall our trig identities. Now, I'm not talking about the more obscure ones. I'm just talking about the fundamental ones, the basic ones that you really need to have down. What can we do at the top there? Well, notice that we've got a bunch of cosines, and then we've got this one sine expression. Remember how, if possible, we generally want to write everything in terms of the same trig function? And we can turn that sine squared into an expression of cosine, right? You recall which basic trig identity that is? That's going to be our Pythagorean identity, right? So instead of writing a sine squared x, the Pythagorean identity is the one that says that you can replace it with 1 minus cosine squared x. Again, the bottom still just coming along for the ride, waiting for us to acknowledge it and do something with it. 0 or undefined. All right, let's distribute out that top and cross our fingers and hope that there are some like terms that we can combine. So we'll get cosine x plus cosine cubed x. And I distribute that, I get 2 cosine x minus 2 cosine cubed x, all over the bottom, equals 0 or undefined. And let's combine those like terms. Cosine x plus 2 cosine x gives us 3 cosine x. Cosine cubed minus 2 cosine cubed gives us minus cosine cubed of x, all over the bottom. Again, I know it gets tedious writing some of the, like the bottom, the denominator, and this 0 or undefined. I mentioned in class that if you want to put a little scribble or something in the bottom, just put some kind of placeholder to make sure that you don't completely forget about this. All right, what now? Well, let's factor the top, because remember, after we combine like terms in the numerator, it's pretty common practice to try factoring algebraically. So up top, we've got a cosine x. And what's going to go inside these parentheses? How about 3 minus cosine squared of x, all over 1 plus cosine squared x squared. And now we're about at the point where we can finally start coming up with some critical numbers here. Okay, pause, take a breath if you need to. Our next step is to say, okay, what exactly are our critical numbers? What's going to make this derivative, and I'll put the reminder there that this is f prime of x, what's going to make this derivative equal to 0 or undefined? Well, let's take a look at the denominator. If this function is to be undefined, then that means that the denominator has to be 0, right? Notice that the denominator can't possibly be 0. Whatever cosine of x is, when you square it, it's going to become a positive number. And then you're going to add it to 1 and then square it again. There's no way within the real number system that that's ever going to be negative, right? So we're not going to have that undefined case. So even though I stress that you need to write the denominator every time and not forget about it, in this case I'll acknowledge that this denominator didn't yield any critical numbers. What about making this derivative 0? Let's look at this factor first and use some similar reasoning. That the biggest that cosine can ever be is 1, and the smallest it can be is -1. Either case, when you square it, we convince ourselves that cosine squared of x will never exceed 1. And so if you're subtracting a number which is at least or at most 1, if you're subtracting that from a 3, you're never going to get a negative a 0 from that. Cosine squared of x could never equal 3. Okay, so we're not going to get any critical numbers from here. That leaves just this. When is cosine of x going to equal 0? We use our unit circle knowledge, and we know that that happens. And remember, we're working on the interval from 0 to 2 pi, right? So even though there are technically an infinite number of x values where cosine of x will be 0, we're only going to count the pi over 2 and the 3 pi over 2. And those are what we'll call our critical numbers. Those are within the domain of the function, I'll point out. So we've had that issue in previous videos where we got something that looked like critical numbers, but they weren't in the domain of the function. Well, these you can plug in to the original, and you can get real outputs. So those are actual critical numbers. So let's proceed with the first derivative test. Again, if I draw our number line, instead of going from -infinity to infinity, again, one more time, we're working on the interval from 0 to 2 pi. And then within that, I've got a pi over 2 and a 3 pi over 2. So for my first derivative test, our first interval will be from 0 to pi over 2. And then from pi over 2 to 3 pi over 2. And then from 3 pi over 2 to 2 pi. Those are our three intervals. And I probably explained in class how with trig functions, sometimes I like to do without an official test value. I'm going to leave that for the classroom. I'm going to go ahead and pick a test value here. Let's say between 0 and pi over 2, we'll do pi over 4 in the first quadrant there. Pi over 2 and 3 pi over 2, we can pick any angle in this quadrant, second quadrant, or third quadrant. Why don't we just pick pi? And how about 3 pi over 2 to 2 pi? Let's pick, that's going to be in the fourth quadrant. How about we pick that angle, 7 pi over 4? Okay, now we need to find the sine of f prime. And I've copied f prime from our earlier work. I've copied it down here. And we're in a bit of luck here because remember from the earlier discussion that we made the argument that that denominator will always be positive. And we also made the argument that cosine squared could never be greater than 1. So we can make the argument that this expression here will always be positive as well. So that's going to make our job a lot easier. So if I want to test my first test value, pi over 4, I just look at this and I say that is clearly going to be positive. So I'll put a positive here because positive times positive over positive will give me positive. If I put a pi here, this becomes negative. So this will be negative. And finally, if I put 7 pi over 4, I'm back to positive again. So as far as my conclusion goes, let's get rid of that. We know we have a function that is increasing with that positive f prime, and then decreasing, and then increasing again. And the values at which it changes directions are those critical numbers pi over 2 and 3 pi over 2. So this will be a local max. Scroll down here just a little bit. There'll be a local max at pi over 2. And here we'll have a local min. And that will be at 3 pi over 2. Oops, I almost forgot that we're supposed to specify the intervals of increasing and decreasing. So there you have it, summarizing what we previously discussed here. And if I were to plug those values back into this original function, I would get a 1 here and a negative 1 here, and those would be my extrema. So to close, let me bring up a GeoGebra representation of that function. And there it is between the intervals of 0 and 2 pi. And if I were to show what the f prime graph looks like, or let's point out that the extrema are where we expected it to be at pi over 2 and 3 pi over 2. And I'll point out, by the way, that here's a depiction of the f prime graph. And I want you to notice how that kind of looks like the pictures that we got from our first exercise. So take a mental snapshot of what you see on the screen right now. And notice that it has some similarity to what you see from our earlier exercise. If we had had more smooth transitions going on there, if we didn't have the sharp points, if they had been smooth there, then we would have had a continuous f prime graph, and it would have looked more like what we saw in the GeoGebra picture there.